Hey guys, my name is Robin Stafuric. I'm a chemistry teacher over at Davidson High School, and today I'm going to continue where Ms. Legrone left off with chemical reactions, and I'm really excited to do this, so hopefully we'll have a good time with it. All right, so let's get started. So last week with Ms. Legrone, you talked about the different components of a chemical equation. So reactants, products, the different states of matter, solid, liquid, gas, aqueous. And today we're going to put that all in some balancing as well. She also went over with you. We're going to pull in some more balancing, making sure we're following the law of conservation of mass. And we're also going to look at the different types of chemical reactions. Okay? So there are 5 types of chemical reactions that you will be dealing with in a chemistry course. All right? Synthesis is the first one. Decomposition, combustion, single replacement, also sometimes called single displacement, and double replacement, also sometimes called double displacement. All right, so we're going to talk about each one of those in a little bit. All right, so let's see. For a synthesis reaction, this is your general formula. So when 2 or more substances react to produce one product, that's your key there, one product. All right, whenever you see something, if they give you a test question, they said, which one of these is a synthesis reaction? You say, which one only has one product? All right, so you have 2 or more reactants, which are on the left side, one product, which is on the right side. So when we synthesize something, we make something. All right, so here are some examples. We have iron and chlorine gas. When they come together, they make iron 3-chloride. You have sodium and chlorine gas, which together will make sodium chloride. You have calcium oxide and water, which makes calcium hydroxide. And you have magnesium metal and oxygen, which will make magnesium oxide. As you can see, they follow the general form in which there is one product. And sometimes you can even have more than one reactant and still have one product. Okay? Now, the opposite of synthesis is going to be your decomposition reaction. So it looks kind of like a synthesis reaction, just flip-flopped. All right? So when a single compound breaks down into 2 or more compounds, so we're decomposing it. All right? Note once again, this is the exact opposite of synthesis. All right? I know my students have a test question coming up that they have got to know that the opposite of a synthesis is decomposition and vice versa. So the telltale sign for decomposition is that you have one reactant and 2 or more products. All right? And then looking at some examples here, we have sodium nitride, which will break down into sodium and nitrogen gas, ammonium nitrate, which breaks down into dinitrogen monoxide and water, and then water, which can break down through electrolysis to hydrogen gas and oxygen gas. All right, so let's see. Now the third type is combustion. Now a combustion reaction, you saw one of those reactions with Ms. Legrone, who reacted some butane, and we'll talk about that reaction in a minute. But how you know you have a combustion reaction is you're going to have a hydrocarbon or some other kind of, hydrocarbon usually talks about a hydrogen and a carbon. All right, you could also have a hydrogen, a carbon, and an oxygen. And you need oxygen in a combustion reaction. So think whenever you have a combustion reaction, you think of fire, you think of flames, and you have to have oxygen to feed that fire. Okay, so your products with the combustion reaction are always going to be CO2 and H2O. So really the only thing that changes in a combustion reaction is the fuel or the hydrocarbon or the carbon, hydrogen, and oxygen that are being used as one of the reactants. The O2, the CO2, and the H2O are going to remain the same. They just are going to be balanced differently. Okay, so here we have an example. So methane, which is natural gas, when it reacts with oxygen, is going to produce carbon dioxide and water. And then we have methanol, which is kind of the alcohol version of methane, which is going to react with oxygen to make CO2 and H2O. So once again, the telltale sign for this is you see the O2 as one of the reactants, and then you have your 2 products, which are always CO2 and H2O. All right, now, I will admit, balancing combustion reactions can be tricky. I don't even like balancing combustion reactions. Sometimes it takes me a second. So we're going to do some more practicing with balancing like you started with Ms. Legrone right now with combustion, okay? So this is a fail-safe way to actually get through a combustion reaction. We're going to do these together after I say what we're going to do. So we're going to put 2 in front of the hydrocarbon to start, And then we're going to balance the carbon, hydrogen, and oxygen in that order. First carbon, then hydrogen, then oxygen. Make sure the answer is in the lowest whole number ratio, because sometimes since we put that 2 in front of the hydrocarbon, it might only need a 1. So we might have to reduce everything by 2. All right, so we're going to do 1. This right here, C2H5OH, is methanol. And what I did is I rewrote it over here to make it a little bit easier by combining the hydrogens. All right, I like everything to be kind of stuck together. All right, so we have 2 carbons here, 6 hydrogens, 1 oxygen. So let's go ahead and follow what we have here. Put a 2 in front of the hydrocarbon to start. Okay? Now, when I teach my students this, and this is not necessary when you balance, but sometimes it's nice when you first start to set up this little chart, so to speak. So now we have 4 carbons. All right? We're going to have 12 hydrogens, and we're going to have 2 oxygens. Okay? Now we're going to go ahead and we're going to balance, like we said, in order, the C, the H, and the O. So we have 4 carbons here, so we're going to put a 4 over here in front of this carbon dioxide. So that gives us 4 carbons, and then we're going to have 8 oxygens, okay? Because when you put a coefficient there, it's going to distribute to the different subscripts, all right? So now we're going to look at the hydrogens. So we have 12 hydrogens over here, because we take the 2, we multiply it by the 6, and we come over here, and we have a 2 right here. So if we put a 6 in front of the hydrogen, now we have 12 hydrogens. So our carbons are now balanced with 4 and 4 on each side. Our hydrogens are balanced with 12 and 12. Now we got to do the oxygens. Now, don't forget that when we put that 6 in front, we've also got to multiply that by this understood 1 for the subscript. So that's going to be 6 right there. Now for the oxygens. So over here, we have 8 plus 6. So we're going to have a total of oxygens of what? 14 over here. We already have 2 right here. All right? So that leaves 12 left to be placed here. Well, if there's already 2 oxygens here, and we put a 6 right there, these oxygens here are going to be 12. So now we have 12 and 2, which is going to give us 14. So it is balanced. However, like in math, when you have to reduce your fractions, we're going to think of our coefficients similarly. 2, 6, 4, and 6. These can all be reduced by 2. And that's what we're going to do. So that's going to make this, I'm going to write it down, I'm going to cross them out, but then I'm going to write it down so it looks a little neater. So this would be 1. 2 divided by 2 is 1. 2 into 6 is going to be 3. 2 into 4 is 2. 2 into 6 is 3. So our final answer, when this is all said and done, the coefficients are 1, 3, 2, and 3. I'm going to erase that just to make it look a little neater. Now I got to remember what I said. So we said that was 1. We said this was 3. This is 2. This is 3. So there's your balanced equation. Takes a little time, but it's worth it and you'll get through it, I promise. Okay? Now, one other kind I just want to show you real quickly is what Ms. Legrone did last week when she did her, she made bubbles that were flammable, and then she lit them on fire and they went up, okay? That was, I believe that was butane she was using. Was she using butane or methane? I'm not sure, but that was a type of combustion reaction that she was doing last week. So they give off a lot of heat, so they're very exothermic, all right? Now, one other type I wanted to show you for combustion is, and you don't think of combustion this way, but cellular respiration is a type of combustion. So if you're a biology buff, this is glucose plus O2 yields CO2 plus H2O. So in your cells, we take in glucose. This is glucose. That should be a 6, I'm sorry. Okay? And in the cells, so that we intake glucose with what we eat, and at the cellular level, our cells use the glucose. Oxygen we bring in when we breathe, and then we breathe out CO2, and our cells absorb the water. Okay? Now, just to make sure we have enough time for all this, I'm going to go ahead and show you what that would look like balanced, simply because I don't want to run out of time. So this would be a 1, a 6, a 6, and a 6. And if we have time, we can come back and balance that one. I just want to make sure we get through all of our reactions so I don't spend too much time on combustion. All right? So that's cellular respiration, which is another type of combustion reaction. Okay. So like I said, if we have time, we can come back and work on balancing that one, which can be kind of a bugger. All right, moving on. Let's look at single replacement. So a single replacement reaction, you have a compound on the reactant side, and then you have an atom, or you have an element, or you have a diatomic molecule, all right, depending on if it's a metal or a non-metal. But you always have one thing and then two things here. So you have an element or a diatomic molecule and a compound, all right, and they're going to swap each other out. The one that's by itself is going to try and swap out whatever species is over here that it matches. So if this is a metal, it's going to try and push out the metal, which would be your cation, okay? If it's a non-metal, it would try and push out the anion, which would be your non-metal, all right? So let's look at that. I have some examples here. So now this might look strange to you, the HOH, that's water. A lot of times when we do single and double replacement reactions, it's a lot easier to write water as HOH because you can see the hydrogen acting as a positive cation and the OH as a negative anion. So lithium plus water gives you lithium hydroxide and hydrogen gas. Copper will displace the silver because they're both metals and create on the other side the silver by itself and then the copper nitrate. Okay, notice lithium can actually kick out hydrogen. Why? Because hydrogen can also be a cation or an anion. In this case, when it's out front like that, all right, it's going to be positive. So in water, when we think of water dissociating, and when we think of acids, the hydrogen's out front. All right? So the lithium is able to kick out that hydrogen because they're both cations. All right, so let's do some more examples of that, and we're going to talk about the reactivity table and why that's important. Okay, so this is an activity series, which I sometimes call a reactivity table. You have decreasing activity, and on this side you have your nonmetals, your halogens, which are typically what's involved with these reactions. These are your nonmetals. Over here are your metals, but notice hydrogen is in there as well because hydrogen can act as a cation, so it can be displaced by metal. All right, so let's see what we got here. So we got to make sure here we go. For a single replacement reaction to occur, the element that is by itself has got to be more reactive or stronger, if you will, to kick out the one that is bonded. All right? So using the activity series is going to show you the relative strength of these elements. All right? So once again, in order for the reaction to occur, the lone element must be above the element in the compound. It must be more reactive. Otherwise, there's no reaction, or NR. So let's try that out. Eventually, we're going to try that out. And you need to remember, and I already mentioned this, but just to reiterate, all right, a metal can replace another metal because a metal solid is going to become an cation when it is in the compound. And a halogen, which is a nonmetal, can replace another halogen or a nonmetal because they're the anions. All right? Now, here we go. All right, so this question says, for the following reaction, is it going to occur? So we have to consult our activity series, or reactivity table, like I call it, which I'm not sure if that's 100% right, but that's what I call it. That's what my kids know. All right, so if we have silver plus copper, copper-2 nitrate, will this reaction occur? So this is a metal. It's going to displace the metal because those are your cations. This is not a cation now, but when it's paired with the nitrate, it will. All right? So that's what we want to see is going to happen. We want to see, is this strong enough to kick out that copper? Meaning, is the silver above the copper on the activity series? All right? Because this is decreasing activity. So we look right here and we see silver and we see copper. Copper is actually above silver or stronger than the silver on the activity series. So this is a no reaction. No reaction. This is not going to occur because this is above silver. All right, now on the example that was a little bit earlier, on the few slides earlier, you had copper plus silver nitrate. So if we switch out the two metals and say, but can copper displace the silver? We say, well, copper is above the silver, so yes, it can. So it would kick out that silver. All right, now we know from this that copper would have had to have a charge of +2, given how it's paired with the nitrate. All right, silver is always going to be a +1 charge. All right, so this should actually be like that. Sorry, my bad, guys. Looks like that. Okay, because this is going to be a -1 charge, this is a +1 charge. We don't need the parentheses and 2. My bad. Okay, so the copper would displace the silver. So you'd have silver metal and then the copper nitrate. Okay? And then if we needed to balance that, so this will occur, this reaction will occur. And then to make sure we have the right amount of everything on each side, we have 2 nitrates here, we only have 1 here. So we're going to need a 2 in front of the silver nitrate. That 2 would carry on to the silver as well, so we need a 2 in front of the silver solid. All right? So that's what that's going to look like. So let's look at another. So will this reaction occur? So we have magnesium, we have aluminum. Magnesium would form a cation. It's going to displace the cation, which is the aluminum. All right? So we find magnesium, which is pretty high up here. And then aluminum is right below it. It's pretty high up there too, but it is below the magnesium. So magnesium is strong enough and reactive enough to kick out that aluminum. So this reaction will happen. What that would look like, and whenever you do these, you want to make sure you have your periodic table available, simply so you can look at it and get your oxidation numbers. All right, so aluminum chloride, the magnesium is going to come in and kick out the aluminum, so the aluminum will become a solid. All right, now magnesium has a charge of +2 when it's an ion. So magnesium with a +2 charge and a chlorine, so this has a +2 charge, this has a -1 charge. So the 2 is going to be right here. It's going to take 2 chlorides with a charge of -1 to balance the 1 magnesium with a charge of +2. All right, we get rid of those because we don't want them. Once they're together, they're neutral. Okay? So with that being said, now we've got a balance. So we've got 2 chlorines here, but 3 chlorines here, because aluminum has an oxidation number of +3. So what we're going to need to do is balance out these chlorines first. We'll put a 2 here in front of the aluminum chloride. We're going to need a 3 over here in front of the magnesium chloride. So now the chlorines, there are 6 and there are 6. All right, for the aluminums now, we have 2 here, but only 1 here. So we need a coefficient of 2 there. Now we have 3 magnesiums here, but only 1 here, so we need to put a coefficient of 3 right there. And now you're balanced. And we don't need to reduce it, so we're good to go. All right, moving on. Will this reaction occur? So we have a halogen here, and we have the bromine, and it's not going to displace the magnesium because bromine is a nonmetal or a halogen. It wants to displace the halogen. All right, so we look at chlorine and we look at bromine. Chlorine is above bromine. Bromine needs to be above chlorine for that to happen, but it's not. So this reaction would not occur. This would be a NR or a no reaction compound. All right, so I'm going to show you one more, and then we're going to go into double replacement reactions. So let's look at if we had, actually I might show you 2 more, and then we'll go through the double replacement. So if you had, let's say, F2 plus MgCl2. Now that 2 is not there because it's a diatomic molecule. It's there because the charge of the magnesium is +2. The chloride ion is -1. All right? But fluorine is above chlorine. So the fluorine would go in, kick out the chlorine. Chlorine is a diatomic molecule, Cl2 plus magnesium F2. That 2 is there because fluorine's a -1 charge, magnesium's a +2 charge. It takes 2 fluorides to balance the charge of 1 magnesium. All right? So that is an example of one that would happen. Okay, one last thing, and then I'll be done with my single replacement reactions. Zinc plus HCl, whenever the hydrogen is in front, that means it's going to be a cation. So the zinc can actually go in. Here's zinc, here's hydrogen. It can kick out the hydrogen. So the zinc will come in, replace the hydrogen. Hydrogen is a diatomic molecule, so there's going to be two of them when it's by itself. Zinc is like silver. It only has one oxidation number for its, it's a transition state with a transition element with only one oxidation number. So it's 2. So whereas silver is +1, zinc is going to be +2. So this would be zinc chloride like that. Okay, now we just need to balance. So if we put a 2 in front of the HCl, we have a balanced equation. 2 Cl's here, 2 H's here, only 1 zinc, we're good to go. All right, last one. Double replacement. So a double replacement has a form, compound plus a compound yields compound plus a compound. All right, so it's going to be exchange of ions between the two compounds. All right, so let's see what that looks like. We have sodium carbonate and silver nitrate, which make sodium nitrate and silver carbonate. We have the one that Ms. Legrone showed you last week, which was the 2 clear liquids that she came together and got a bright yellow liquid. That would have been the lead iodide. All right, so lead 2 nitrate plus the potassium iodide is going to yield lead 2 iodide plus potassium nitrate. All right, and you can see compounds, 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 compounds. All right, let's see. In order for a double replacement reaction to take place, one of 3 things must be formed. A solid, also called a precipitate, gas, which you'll see as bubbles, or a weak electrolyte. A weak electrolyte would be an example of a weak acid, a weak base, or water, okay, which conduct some current because of the positive and negative charges that are partly dissociated, but not a lot of current. All right, let's see if we have time for one. I'm going to skip over this one because this should be something different, so we're going to do this next one. And we can correct the next one if we have time. So hydrochloric acid reacts with calcium hydroxide. This is actually a neutralization reaction, which is a type of double replacement reaction. So let's try that real quick and see. Hydrochloric acid is HCl plus calcium hydroxide, which is CaOH2. Remember, hydroxide is a -1 charge. The 2 comes from the +2 on the calcium. Now, what's going to happen is the cations are going to replace each other. So you end up on the other side with calcium chloride plus HOH, which is actually water, H2O. But it's kind of easier to think of it as a hydroxide and a hydrogen in problems like this. And this is a type of double replacement reaction. This is a neutralization reaction, which produces water and a salt. A salt is just in the neutralization reaction, the hydrogen comes from the acid, the OH comes from the base, and then what's left goes into the salt. So if we balance this, we say, all right, well, we have 2 OHs here, so let's put a 2 in front to make this 2 OHs, all right? And we have 2 chlorines here and 2 more H's. So if we put a 2 out front here, we're balanced, all right? So that is not only a double replacement reaction, but also a reaction in which you have a neutralization going on as well, okay? So I would love to do more. I actually had some more practice. I'm sure you guys would love that, but we're going to have to wrap it up soon. And I just want to let you know, for next week, make sure you have your calculators ready because we are going to be doing the mole, not a fuzzy brown animal that lives underground, but an amount that we use in chemistry, all right? So bring your calculators and be ready to learn some great stuff with moles. Thanks, guys. Have a good day.